Hello, I am Apurva Nakade, and this is my research statement. Let me start by thanking the organizers for providing such a wonderful opportunity, not just to me, but to everybody who is in the job market right now. This is me. I am at the end of my 2-year postdoc at the University of Western Ontario. My current advisors are Dan Christensen and Chris Kapolkin, and my PhD advisor was Nitu Kichlu. I did my PhD at the Johns Hopkins University. I will be applying to liberal arts colleges and teaching track positions. And here's my website, just my name at github.github.io. And you can find more information like my CV there. My research is mostly in homotopy theory. These are the projects that I'm currently working on. Two groups. There are two projects and two groups that I'm working on. Then computer-assisted theorem proving. And in the past, I was interested in equivariant embeddings calculus. This is something I'm still interested in, but not actively working on. I'll just focus on the projects that I'm currently working on in the following slides. Let me start by explaining what a two-group is. Two-group is, you can think of a two-group as a group with a weaker notion of associativity. In a group, our multiplication is associative, that is xy times z is the same as x times yz. But in a two-group, we weaken this by requiring that xy times z is not equal, but instead is isomorphic to x times yz. Now, of course, it doesn't make sense to talk about isomorphisms inside a group. So you had to change the underlying set to a monoidal category or a bi-category to make sense of this. But it's enough to think of a two-group as a group with weakening of associativity. And this isomorphism, which can be captured using a third cohomology group element, we'll call this alpha, with coefficients in some module. You don't need to know what a group cohomology is. It's just the data of this isomorphism. Just to summarize, given a group and a third, going in the other direction, given a group and a third cohomology element, we can construct a two-group out of this data. And we'll denote two groups by script G. Now, this is my first project on two groups. It's about finite Chern-Simons and two group bundles. This project started at an AMS workshop, an MRC workshop, Math Research Communities. And this is joined with people from all over the world. And in this project, we show that the Freed-Quinn line bundle for discrete groups can be identified as a bundle of two groups. And I'll explain this in more details. That paper called Chern-Simons theory with finite gauge group, Freed and Quinn define a line bundle or MGX, which I'll describe below. So we start with the data of a Riemann surface and a finite group G and a third group cohomology element. So the group cohomology element shows up again. This time the cohomology element takes values in U1. And here MGX is the groupoid of isomorphism classes of flat principal G bundles. It's just some, so you're starting with a Riemann surface. Then on this Riemann surface, you're looking at all the possible principal G bundles. And this forms a stack. But for this talk, I'll just think of it as a groupoid. And then on this groupoid, the collection of all principal G bundles, I'll define a line bundle. And I'll do that using a third group cohomology element. And this is called the Freed-Quinn line bundle. And the sections of this line bundle have something to do with Chern-Simons theory for finite gauge group. So that's their construction, classical. In our work, we show that this whole construction, this two-step construction, is actually nothing but a two-group construction. So we show that this line bundle can be identified as the space of flat script G bundles. Script G is the two-group corresponding to G and alpha living on X. And so what we're seeing is that two groups which are bi-categories or higher categories are actually fundamental in physics. They show up naturally in Chern-Simons. And the way we prove this is by explicit constructions. We find like the transition functions of L using the first direction, the black direction, and then using the second direction and show that both the transition functions agree. So that is our first main result. And it's a lot of fun calculations. Is now where to go from here. So far we have identified what this bundle is, but now we want to go further and look at all these line bundles together. So study the collection of these script G bundles on the moduli space of all Riemann surfaces instead of one fixed Riemann surface. And maybe there is a product on this. So maybe there is an algebra or co-algebra structure that we could see when we look at all Riemann surfaces. We are also interested, like I personally am interested in computing invariance of these two group bundles. Like, are there Chern classes? Can we classify these line bundles using an invariant? And I think this has a lot of potential for undergrad research because you can define Chern classes for line bundles very explicitly using transition functions and determinants and traces of matrices. So that is all I have to say about my first project. My second project is on homotopy type theory. What is homotopy type theory? Homotopy type theory is a type of axiom system that provides an alternative to the standard ZFC set theory. In set theory, sets are the fundamental objects and topological spaces are built out of sets. But in homotopy type theory, the direction is reversed, and topological spaces are the fundamental objects and sets are built out of these. Homotopy type theory provides a natural space to do homotopy theory. And here's the most important thing about homotopy type theory, that its proofs are computer checkable. They can be rigorously verified without a shadow of doubt. It's a double-edged sword. That means that it makes it harder to write proofs because you can no longer be vague in your statements. This is my project. It's two groups in homotopy type theory, and this is joined with Dan Christensen. Now, in homotopy type theory, a two group is defined as a topological space, or as a homotopy type, whose homotopy groups are concentrated in degrees 1 and 2. So this is very different from what we saw earlier, where you had a finite group G and cohomology class alpha. But the main result of this project that we show is that this new definition is the same as the old definition. That is, two groups in homotopy type theory are the same as two groups in classical theory. That is, the type of two groups whose one truncation is BG is equivalent to the sigma type, whereas phi you can think of as defining A as a G module and then looking at all the possible third cohomology elements. So we are saying that these two walls of homotopy type theory and set theory agree on the notion of two groups. And the proof is by constructing explicit equivalences. Future directions, I am interested in trying to see if we can extend our current results to bundles or Riemann surfaces. But first, I need to figure out if it's possible to define Riemann surfaces in homotopy type theory. Because homotopy type theory is very rigorous and it is homotopy theoretic, I need to figure out a homotopy theoretic characterization of a Riemann surface. And I'm also interested in extending this result to higher groups. And both of these projects have very little prerequisite. You need to know some basic things in homotopy type theory, but really Riemann surfaces and higher groups are very elementary objects. And this is a lot of potential for undergrad research. Then the last thing I want to talk about is computer-assisted theorem proving. This is something I got interested through homotopy type theory. Because I was doing homotopy type theory, which is very naturally proof checkable, I got interested in proof checking as its own field of research. And I'm interested in the lean programming language, which is very actively developed. I taught a course on this over the summer, and this is a website you can see here. And my current goal is to add more math to the existing library of lean. The lean library called mathlib is a vast library that contains a lot of existing mathematics, but it's still lacking in many areas, especially in analysis. And I am trying to help out with adding more math to the library. And much of this math is being added by undergrads. If you know the math, learning lean is not hard, and you can just try to encode that in lean and then put it in the math library. In the future, I am interested in using lean as a teaching tool to teach math. Right now, the direction is the other way. If you know math, then you can try to code it in lean. I think personally that lean could go in the other direction. That is, it might be possible to create a software which gives students immediate feedback on their proofs. Another thing I'm interested in is using AI and lean to auto-generate theorems and proofs. This is something in the far future, not something I'm currently working on. Yeah, so that is my research statement. Thank you very much for your time.